So before we talked about how to identify whether a relation was a function or not, and we said that each input has to have exactly one output. And we talked about our vending machine. If I type in A2 and I'm expecting a Kit Kat, I want to get that Kit Kat every time. If I type in A2 and sometimes it gives me a Kit Kat and sometimes it gives me Reese Cups, that's not a function. We have to know exactly what we're going to get. Today we're moving into linear versus nonlinear functions. You see that word linear has a line at the front. Linear functions are just a straight line. Nonlinear means that they're not going to be a straight line. So all that is, we've graphed lines before. Those lines that we graphed were examples of linear functions. So let's start filling in the blanks. A function that is linear will have a constant rate of change and can be distinguished from nonlinear functions in each of the following representations. So if you look down at these three sections here, it says linear equations can be written in the form of y equals mx plus b. And we've seen that before, right? This is our slope-intercept form. Remember that m was our slope and b was our y-intercept. So if we have an equation in slope-intercept form, we know it's going to be linear. Looking at a table, a constant rate of change. So what we're looking for in a table is a constant rate of change. And that means as the x values change by a constant value, the y values will also change by a constant value. So for example, in this table, from 0 to 3, there's a difference of 3 there. We're going up 3 there, we're going up 3 there. So my x's are increasing by a constant value. Let's check the y's. So from 2 to 4 is 2, 4 to 6 is 2, 6 to 8 is 2. My y's are also increasing by a constant value. So this one would be linear. And remember when we were using our tables for graphing those linear equations or writing the equations, this y over x or 2 over 3 would be our slope because it's our constant rate of change. Alright, as for linear graphs, it's just that the graph will form a straight line. So anytime you see a perfectly straight line, you know it's a linear function. Alright, looking down at 1 and 2, we're going to determine whether these equations that they gave us form a linear function. So first step, we're going to fill in the table. So we're given this equation, this y equals 1/2 x, and we need to figure out from this table, if I know my x values, what are my y values? So I have xy. This is an x in my equation, or my graph. I can plug this -4 in for x in my equation. So if I do y is 1/2 times, plug in that x, -4, half of -4 is -2. Then I can do the same thing with this -2. So if I plug in -2 for x, 1/2 of -2 is -1. Half of 0 is 0. Half of 2 is 1. Half of 4 is 2. So there's how we can fill in our tables. In our tables, if we notice this one goes up by 2, up by 2, up by 2, up by 2. So my x's are increasing at a constant rate. My y's, down 1, or up 1, up 1, up 1, up 1, they're increasing at a constant rate. So now we can plot these points. So I have a point at xy. So -4 is my x, -2 is my y. Plot that point. Remember, this is my x-axis, this is my y-axis. I have a point at -2, -1, 0, 0, 2, 1, and 4, 2. So is this function linear? The answer is yes. And that could be for several reasons. Because we didn't really talk about it, but this equation up here is in slope-intercept form. That 1/2 would be our slope, then x, then plus b. Our y-intercept would just be 0. So we're good there. So yes, we could say something about the equation is in y equals mx plus b. We could say the graph is a straight line. Let's scroll this up. Graph is a straight line, or the table shows a constant rate of change. Sorry the handwriting's so bad at the bottom. My tablet does not like when I write at the bottom of the screen. Alright, now looking at number 2, let's do the same thing. So I have this equation. First of all, what do we notice that's different about this one than any of the other equations we've used to graph lines before? This little squared up here. So we have x squared, so that's making me think this might be a little bit different. So again, I'm going to plug in each one of my x's in for x here. And when we substitute any values, it's important to put parentheses around them, especially if you're squaring a negative number or using any kind of exponents on a negative number. Because, real quick, I'll do something off to the side. If I have -2 in parentheses squared, that's the same as -2 times -2. And -2 times -2 is +4. But if I do -2 squared without parentheses, that's the same as -2 times 2, which is going to be -4. So they give me two different answers. So make sure your whole x value is -2. It's not out front, it is all together. So put it in parentheses so you make sure you get the right answer. Alright, so -2 squared is 4, plus 1 is 5. And the same thing, plug in -1 for x squared. -1 times -1 is 1, plus 1 is 2. 0 times 0 plus 1 is 1. 1 times 1 plus 1 is 2. And 2 times 2, or 2 squared is 4, plus 1 is 5. Then we can plot these points. So I have -2, 5, -1, 2, 0, 1, 1, 2, 2, 5. Then again, is this function linear? No, obviously not, right? It forms this curve, and eventually we're going to learn either next year or the year after probably that that's a parabola whenever you get into algebra. And this is nonlinear because it's a curve. And again, down here, I'm not going to write it all out, but we could say the exact opposite as last time. No constant rate of change, no y equals mx plus b, no straight line. I'm just going to say does not form a straight line. Alright, I want you to pause the video and take a couple minutes to try to fill out these tables. Then I'm going to go ahead and fill them out so you can check your answers. But just know, same thing, we're plugging in all of our x's to our equation. Make sure we know that x cubed, it's not -2 times 3, it is -2 times -2 times -2. -1 times -1 times -1. Each number multiplied by themselves 3 times. But yeah, then you come back, we'll check our answers, and then we'll move to the bottom.